We have another example problem here. We have a 20 centimeter diameter cylinder that is 40 centimeters long. It contains 50 grams of oxygen gas at 20 degrees Celsius. We want to find how many moles of oxygen are in the cylinder, how many oxygen molecules are in the cylinder, and what is the reading of a pressure gauge attached to the tank. All right, so our cylinder. The diameter is 20 centimeters, so the radius is 10 centimeters. It's 40 centimeters long, so H is 40 centimeters. We have 50 grams of oxygen gas, and our temperature is 20 degrees Celsius, which I'm going to go ahead and put this into Kelvin. So 293 Kelvin. Alrighty, so the dimensions of the cylinder will allow us to find the volume. The gas is going to occupy all of the space in the cylinder. So the volume of a cylinder, this is on the back cover of the test notes, if you don't happen to remember the volume of a cylinder. So pi, our radius, we do want this in meters, and the length in meters, so that we are ending up with our volume in meters cubed. So 0.01257. I'm keeping a few digits because I'm not at an answer. Now, 50 grams of oxygen gas. Oxygen gas is one of those diatomic gases, meaning two oxygen atoms bond together. Since we're given a mass, we want to look at the periodic table. So let's go back to the test notes here really quick. Oh, there it was. Oxygen is essentially 16. So one oxygen atom is 16 grams per mole. Oxygen gas is a diatomic, so we have 32 grams per mole. I can use that as my conversion factor, 32 grams per mole. I'm going to erase the m equals because that changes what I'm doing. The grams are going to cancel and leave me with moles. So 50 divided by 32 gives me 1.56 moles. Really, we only have 2 sig figs, so I would say 1.6 is my number of moles of the oxygen gas. So this is our answer to part A. Part B, if we have moles, then we can get molecules as well. And that is by way of Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd basic particles, in this case a molecule of gas, per mole. So since I know I'm going to keep the unrounded number, I'm going to use that. When I multiply by Avogadro's number, the moles are going to cancel, and this will tell me how many molecules I have. So 9.4 times 10 to the 23rd molecules is what we have in this container. So this is what we were asked for in part B. Now part C, the reading on a pressure gauge. So gauge pressure is the pressure in the container minus the atmospheric pressure outside. So we need to know the pressure in the container first, and then we can get the gauge pressure. Well, the pressure, we know the volume. I found that first, even though I didn't need it quite yet. So ideal gas law will allow us to solve for pressure. And technically, since we have both the number of moles and the number of molecules, either version of the ideal gas law would be easy to use. One's not any better than the other. I'll go ahead and use this first version just because it's here. Now I'm going to use the not quite so rounded number of moles in my calculation to minimize rounding errors. So my temperature, this one does need to be in Kelvin, which we already found. The volume is in meters cubed. So everything here is in SI units, which is going to give us a pressure in pascals. So I'm getting, and this is what my calculator tells me, which of course I would round this to 2 sig figs if it were my answer. My gauge pressure, I need to take this value minus atmospheric pressure, and I'm getting 201,446. Oops. So 2.0 times 10.345 pascals would be the gauge pressure. If you wanted, this would be approximately 200 kilopascals, if you like prefixes better than scientific notation. But again, I would write it as 200 and not 201 simply because I only have 2 sig figs. So ideal gas law comes into play, but not until part C. The first part has us using the periodic table, so the concepts from earlier in the chapter.